so it's become a pretty mainstream thing. I mean, of course, it's not one mechanism. The idea is that just like any simple man-made machine, the body, does, causes changes its composition and structure as inherent consequences of the body's natural operation, in other words, metabolism. And those changes are harmless for a long time, simply because the body is set up to tolerate a certain amount of that change, which it has to be, of course, in order that we can reproduce before we die. And so it's only after that has all happened, after the damage has accumulated to a level that the body is not set up to tolerate, that we then start going downhill.
Hi everyone, it's Dr. Sanjeev Goel from PKM Labs, and today I have a great guest for you, Dr. Aubrey de Grey. He is one of the OGs of longevity research. He is a biomedical gerontologist who runs the LEV Foundation and is really the ones helping to spearhead the longevity movement. So I hope you enjoyed today's discussion with him, and we'll see you on the other side. So yeah, I'd love to just take our viewers a little bit about your background. I was listening about your history from before. I thought it's very interesting for our viewers to understand, how did you get into aging? Because you're not a biologist.
Yeah, well, I was not a biologist, that's true. My original field was computer science.
Yes.
I worked in artificial intelligence research for several years, and then I met and married a biologist who's a lot older than me. She was already a professor in California, and she was in the UK on sabbatical. And through her, I kind of accidentally learned a lot of biology informally, but I also began gradually to realize that she wasn't interested in aging, and indeed that the other biologists that I was meeting through her were also not interested in it, and that the very few biologists who were interested in it were either not really trying to tackle it at all, or they were tackling it rather badly, I thought. So I thought, well, this won't do, and I switched fields. That was in the mid-90s. And so I got my PhD in biology, and then started having ideas that, were quite well received, and then ideas that were really heretical and not very well received for quite a while, but which have become quite mainstream now. So yeah, that's my history, really.
Yeah. And so if you could take our viewers back again to the early stages of the research. And because this idea, even that aging, I remember when you had talked about, even at that time, you had said, why should we accept aging? Like this whole idea that before we just think that this is very normal. Everybody aged and this was, part of life. But I remember you saying that on the stage, why should we accept that? Like this is really disease and we should be treating that. But I'd love to hear from you.
Yeah, I mean, honestly, it was just a complete mystery to me why people would think that it was something we couldn't tackle. Because, the human body is obviously a machine, albeit a really, really complicated one whose inner workings we don't understand very well. But it's still a machine, which means that it should perfectly well be amenable to manipulation, same as any simple man-made machine is. And so, stopping us from getting sick when we get old is no different than preventative maintenance for a car or an airplane, in principle. And then turning that into practice, of course, was my main eureka moment back in the year 2000, which has guided my work ever since, namely the realization that, yes, we actually did have a sufficiently good understanding of what kinds of damage accumulate in the body that we could actually describe in reasonably detailed terms what kinds of preventative maintenance we would need to develop. And, it turns out that some of those are easier than others, and there's been quite a bit of progress over the years. Most of my work has been focused on the most difficult types of damage, the ones that other people were really neglecting because they had more short-termist incentive structures. Yeah, so that's basically where I went. But the idea that anyone could ever think that aging was just something we should accept has never made any sense to me at all.
Yeah, because it took somebody maybe from outside looking at it, because you're right, maybe because you came from a different perspective. So let's talk about the damage or accumulated damage kind of mechanism of aging. So where is that right now? Like, how do people think about that as one of the mechanisms?
Yeah, so it's become a pretty mainstream thing. I mean, of course, it's not one mechanism. The idea is that just like any simple man-made machine, the body does causes changes to its composition and structure as inherent consequences of the body's natural operation. In other words, metabolism. And those changes are harmless for a long time, simply because the body is set up to tolerate a certain amount of that change, which it has to be, of course, in order that we can reproduce before we die. And so it's only after that has all happened, after the damage has accumulated to a level that the body is not set up to tolerate, that we then start going downhill. And so that means that you've got obviously a certain amount of crosstalk between various processes of damage creation, but only limited crosstalk. So we can be very sure that the way in which we will bring aging under comprehensive medical control is by a panel of interventions, each of which addresses different types of damage.
Mm-hmm.
Then the question is, how many are we going to need, and how easy is it going to be to develop all that? And the answer is we're probably going to need an awful lot of them, an awful lot of things done in parallel. But that's not as daunting as it may sound at first sight, because the types of damage that we see in the body that we have identified over the years fall into a really rather manageable number of categories. I normally list 7 categories. And the purpose of this classification is that for each category, with each of the examples within a category, there is a kind of generic approach to actually doing the preventative maintenance. So, for example, one category is the loss of cells, where cells are dying and not being automatically replaced by the division and differentiation of other cells. And the simple way to address that is by stem cell therapy, which is very generic, right? And of course, different stem cell therapies for different organs will have differences of detail, but they will have many, many things in common. So that once we get 1 or 2 stem cell therapies working really well, getting the next one working and the one after that will take a lot less time and effort, because we'll be able to leverage the knowledge that we have acquired getting the first one working. And the same applies across all of the other 6.
Mm-hmm. And so you think that this idea that of the kind of a wearing down of the system is really kind of we can describe each of the mechanisms kind of falling into that same pathway. Is that what you're saying? Like people talk about
Yeah. I mean, I avoid the term wear and tear because that has the connotation that this damage is kind of not really connected to the way that the body works, whereas it actually is. These are side effects of processes that need to occur. But yeah, I mean, the cool thing about this approach to addressing aging, and really the big reason why I realized that this is going to be easier than slow aging down more than a very small amount, then you have to understand the mechanisms of how damage accumulates and how it's created in really rather a lot of detail. And even then, it's insanely challenging to try to kind of disentangle the creation of damage from the things that we need metabolism to do to keep us alive, and to stop it doing the damage without having unintended consequences. Whereas when we're repairing damage, we're repairing something that is initially inert, initially harmless. As I said, it's only harmful once it gets up to a certain threshold level. And that means that because it's effectively not participating in metabolism during that time, we've got a much better chance of going in and targeting it and eliminating the damage. And we don't need to know all that much about the mechanisms of how the damage was created in the first. We just need to know what the damage is.
Okay. How would you, so something similar would be happening with epigenetic changes. I mean, similar type of changes are happening, and we're looking potentially at finding ways to kind of reverse those changes?
Okay, you've got to be very careful when you look at the concept of epigenetic changes. There are obviously epigenetic changes that are very much part of development and part of cell differentiation. The epigenome is what makes a particular cell type, not another cell type. Epigenetic clocks that have become so popular over the past several years, a type of, side effect of that, sideshow from there, because basically these are loci in the genome that are changing as a result of other changes in the body, and the body is not essentially trying to stop those changes from happening. What that says to me is that these are changes that don't matter. They are changes that are kind of, readouts of things that do matter, but they themselves do not matter. So we won't achieve much by just just reversing those epigenetic changes directly. However, there are other types of epigenetic change that can be thought of more as epigenetic noise, so variations in the epigenetic state from one cell to another, even though those cells are of the same type. And this epigenetic noise is something that we haven't explored nearly as much as we need to yet. There are various people who've identified as a real key and a real, not just a readout, but perhaps something that can actually have causal significance. And what we do know is that epigenetic noise is also something that we may very well be able to deal with. There seems to be sufficient, if you like, informational redundancy in our epigenome that we can, unaccessed redundancy, that if we can somehow, goose the body into accessing that redundancy when it normally wouldn't be, we can achieve rejuvenation. This is essentially what partial reprogramming is, which is a very fashionable area right now.
Yeah, that's right. It means the idea that there's like a kind of a copy of the original early epigenome is still there somewhere, or the cell has the ability to come back to.
Yeah, I don't like to think of it in terms of a copy. I think that's kind of not a good word to use for this. More, it's a case of simply every epigenetic function, every function that is the result of the epigenome is the result a lot of different sites, a lot of different CpG dinucleotides that are methylated or not methylated. I like to give the analogy of a digital image, a photograph. If you a digital image and somehow you impose some process where individual pixels get randomized at a certain rate, then eventually there will be a degradation in how the picture looks to the naked eye. But then, supposing that one were to process that damaged image, for example, just replacing each pixel with a color and an intensity that is the average of the ones immediately surrounding it, right? Then even without any actual information about what those pixels originally were, one will get back nearly all of the quality of image that one had in the first place. One will be able to very greatly eliminate at least the functional impression of the damage that had accumulated in the past. And that is, to my mind, very much what partial reprogramming is doing.
Yeah, that's very interesting. I never thought of it like that. So you're saying, yeah, there's not necessarily that there's a memory of the information or something somewhere kept. It's like you're saying, maybe.
Yeah, I think the word redundancy is a more accurate word.
Interesting. And so when you look at those different, like there's many, you're right, the partial reprogramming is very much in lots in the news now. Epigenomic changes as well. What's really are you looking at as the breakthrough type of mechanisms, or do you think they all need to be addressed together, like you were saying?
At least to a good approximation, I do think they all need to be addressed. The thing is that these things, as I say, there's a certain amount of crosstalk between them, but only a certain amount. So, if you leave some things completely untouched, we're going to die on schedule, right? Even though there will be, these knock-on effects from one type of damage to another, you really have to hit everything to a certain degree. As you will know, I've coined this term longevity escape velocity to denote how fast we need to improve things in order to stay one step ahead of the problem indefinitely. The question, therefore, comes, when will we first achieve longevity escape velocity? A more precise question is, how much progress do we need to make before we have bought ourselves enough time to be able to make the next increment of progress? And I believe we need to get to about 20 years of the health problems of late life, which I think we might be able to achieve in the next 12 to 15 years.
Mm-hmm. Yeah, it seems like it's very much within reach. And it seems like, obviously knowledge is exploding exponentially. So it's sometimes hard to predict what's going to happen. Yeah, but I think I heard you say on another podcast there was a lot of initial pushback from colleagues when you brought up a longevity escape velocity. Why do you think that is? Why?
So there's two things here. First of all, the prevailing dogma within the community, within the academic community, at the time I first thought of this damage repair thing, was not to think that way at all, but rather to think in terms of slowing aging down. And people had more or less given up on that because they recognized how hard it was. But they had not considered the possibility of preventative maintenance. And so I had to work pretty hard to persuade my colleagues this made any kind of sense at all. And a lot of people actually felt that it was, rather unscientific. It took me, the best part of 10 years to really win that argument. And the publication of the Hallmarks of Aging paper in 2013 was really the final, curtain coming down on that attitude to the divide and conquer approach. So it was very gratifying to me, even though some people think they should have cited me and given I should have more of the credit for this. That doesn't matter to me at all. What matters is that ever since that day, I have not had to justify the damage repair concept to my colleagues. So that's all very great. But longevity escape velocity is a whole different matter. And indeed, perhaps a lot of why my colleagues were so resistant to what I was saying for a number of years was because I was not shy about discussing the inevitable consequence, the inevitable corollary of rejuvenation being a plausible way to go, namely that we will be able to carry on doing it over and over again, getting progressively better at it so as to stay one step ahead of the problem. And therefore, that's pretty much certain that, as I used to say, the first 1,000-year-old is less than 10 years younger than the first 150-year-old.
Right, yeah.
That's a slightly complicated way of saying it. And the reason I said it that way was, of course, I wanted to sidestep the uncertainty, the main uncertainty, which is how soon we will get to longevity escape velocity and how old the first 150-year-old actually is today. That's, of course, a very uncertain thing. But I feel that after that, everything is pretty much programmed. We're definitely going to not need to worry about people dying of having been born a long time ago. And that has turned out to be a much harder sell within the academic community, even though to me it's much more uncontroversial and unarguable. The only people who have really come out and said, yeah, this is obvious, Aubrey's obviously right about this, are the people whose background, even though they're maybe prominent biologists now, whose background is in mathematics.
Yeah, that sounds like, yeah. It sounds like there's a lot being tied to we're living in an age of, right, we're technology and AI, we're at the precipice there of super intelligence and all that. So I wonder why do you feel that you must be seeing, obviously, you see all the developments that are happening with scientists in this space. So you must be feeling quite, feeling quite positive that it's within reach. Like these types of changes are now within reach. Like why you said 15 years, 12, 15 years. This is pretty,
well,
this is
right,
going to happen within our lifetime. So I'm just curious that why, you think it's because technology is enabling this? Like why is this happening?
There's no one thing. The main thing is, as you say, I am very much at the coalface, seeing the specific technologies that are emerging. I'm seeing how for each one of them, I'm looking at the details of how rapidly it's progressing and how much further it has to go before it really comes to fruition. I'm also looking at things outside of the science. I'm looking at the regulatory environment and the conversations that are going on to, incentivize modernization of regulatory regimes. Or sidestep them in some other way. And that's going rather encouragingly as well. So, yeah, it's just a gut. Of course, it's entirely subjective. I have to really, acknowledge that I can't know how long it's going to be any more than anyone can. But I feel that my guess is better than most people's just because I'm exposed to all the details.
Yeah, you wouldn't have made that guess 30 years ago, like saying 12 years from then. Like I'm just saying, it sounds like
Right. I did start guessing. I did start giving timeframe predictions about 20 years ago. And I got a huge amount of heat from a lot of my colleagues for doing so because, it's considered to be unscientific to do that. And it's also considered to be politically incendiary to, be perceived as overpromising. But I think an irresponsible attitude to take. I think that we have to remember that we're working on something that everyone's really terrified of and is just trying to put out of their minds and pretend either that it's a blessing in disguise or else that it's like this inevitable natural thing that's woven into the fabric of the universe and we'll never be able to do anything about it at all. If we let that attitude continue, then people will not be interested in helping to accelerate the process of bringing aging under control, and funding will therefore suffer. And, and I've been telling my colleagues this for 20 odd years, and I've had spectacularly little traction. It's extraordinary. But yes, if we go back 20 years, I was saying at that point that I thought we had a 50-50 chance of getting to longevity escape velocity within 25 years from that. So in other words, my time frame has slipped. But the good news is that pretty much all of the slippage happened during the first 10 of those 20 years. There's not been much slippage in the past 10 years. In fact, basically none. A large part of why is because my prediction was always made subject to adequate funding. And funding was very, very much not adequate for those first 10 years. I reckon that we probably only made about 3 years of progress during that time.
Right.
whereas it's much, much better now. The only problem now is that that funding is drastically unevenly distributed. So
Mm.
there are plenty of areas that are getting spectacularly well funded now, where honestly money is not rate limiting anymore. But there are other areas, and of course these are the ones that I focus on because I'm always focusing on the neglected things, that are still really hurting for money.
Right. Because yeah, there are these the you know the commercial ones probably getting funded much more.
Well,
Um,
things that are close enough. So
yeah.
at my previous foundation, our business model was, because we were a non-profit, but our business model was to get donations and work on things for as long as it took to get them to a point where at least a few of the more courageous angel investor types would think that they were worth actually having a go with. And at that point, we would spin the project out as a startup company. And of course, investors tend to write bigger checks than donors do. So that was a way of accelerating the work. We did that half a dozen times. But there's other work that really isn't amenable to that. At LEV Foundation, at my current organization, our main focus is on combining things in mice that already somewhat work, and therefore thereby finding out, the extent to which we can make them synergize, and get an additive benefit. And that's absolutely vital work. We're going to be discovering optimum doses and, antagonistic interactions where things cancel each other out that you wouldn't have expected, things like that. It's got to be done, but there's no IP in it whatsoever because these are either things that are off patent already or they've been patented by other people or whatever. So, it's like it's can only be funded by philanthropy, and it's very hard to get the money in the door. It's not going as fast as it should.
Yeah, so you're saying those things are definitely still need to be done rather than, necessarily the super groundbreaking type research. I mean, that has the separate track, but just the simple things, like for example, comparing, let's say, rapamycin and metformin together or something like that, or these types of
Yeah, so
interventions.
some people are doing that with things like those. Like actually the poster child right now is rapamycin plus another compound called acarbose. But everyone except us is restricting themselves to orally available things, drugs, basically small molecules. And the one from the point of view of other researchers, that's justifiable. It's those experiments are not very expensive. The experiments that we do are a good deal more expensive, and the reason is because we're not restricting ourselves to orally available stuff. We're doing cell therapies and gene therapies. I'm firmly of the view that if one doesn't go into those areas, then one will hit a very clear brick wall. In fact, I don't think one will make significantly more progress than has been made already. Whereas with gene therapies and cell therapies, the sky is absolutely the limit. But again, you can't. I mean, that makes the experiments pretty expensive, and nobody's doing them. Nobody.
Hmm. Right. So currently, like with the current kind of therapies out there, they're potentially only, maybe adding one or few years of life right now. What do you think? Where do you think we're at?
Right. I mean, that's basically what's going to happen. The only significant improvement that one can make to human longevity today, over and above just, living like your mother told you to and not smoking and not getting seriously overweight and having a reasonably balanced diet and getting enough sleep. Other than that, it's really just emulating calorie restriction, which is obviously a very well-known way to extend your life a little bit. It took a long time for me to get my colleagues to fess up to the fact, which had been swept under the carpet appallingly, that calorie restriction just works much less well in long-lived species than it does in short-lived species, for perfectly easily explainable evolutionary reasons. Essentially simply that long famines are less common than short famines. So yeah, that's it. We're not going to do better with a drug that emulates calorie restriction than we would with calorie restriction itself. And that's all we can do right now. And it's all we're
So
going to be.
things like rapamycin, you think probably won't have that impact in humans. Then you think that's
Well,
been
that's right.
shown.
I mean, rapamycin has about the same impact in mice that calorie restriction itself does. And so it may very well have the same impact in humans that calorie restriction itself does, but that will not be a 40% increase in lifespan the way it is in mice.
Right, 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 right. Yeah, that makes a lot of sense to me. So I know that you're you're doing the Left Foundation, LEV Foundation, but you also run the summits. And I was just coming across the Dublin Longevity Declaration. I just signed it myself just now.
Thank
And
you.
so let's tell our viewers a little bit about that, and why do you think it's time for that?
Yeah.
The dec
Okay. So first of all, the conferences themselves. So I started running conferences 21 years ago. Honestly, not only are they my favorite parts of the year, but also they are absolutely the fulcrum, the centerpiece of all of my community building effort. And of course, I have, put a great deal of my effort into community building, not only into overseeing the scientific progress. So yeah, I mean, I run these conferences with that very much in mind. I make sure that there's lots and lots of time for socializing, lots of encouragement of people to hang out and meet people they've never met before and form new alliances. And this happens all the time. Other conferences have very much followed my lead in that. There's one that I just came back from last week in Copenhagen, which is a particularly successful example of that. But yes, at the moment, these conferences happen in Dublin. They started out in Cambridge in England, where I used to live. And in 2023, the conference launched this thing called the Dublin Longevity Declaration, which is really just a call to arms. Um, as I mentioned, it's been quite hard for me to persuade my colleagues to discuss timeframes publicly, for how soon we might make this or that amount of progress. And the Dublin Longevity Declaration is a big step in that direction. It was really led by myself and my colleague in my foundation, Martin O'D, but with enormous amount of help from Brian Kennedy, another very prominent gerontologist who actually wrote most of the text. It's a much more aggressive statement than anyone had ever written before with regard to not only the imperative, but the likely outcome of putting proper money into the development of therapies that will keep people healthy as they get old. And of course, the key thing about it is that it was actually possible to get most of our colleagues within the scientific community to sign up to it. So the first couple of hundred names are all like, professionals in the field. We definitely want a lot more than a couple of thousand other people to sign up, which is what we've got at the moment. I'd like a couple of 100,000 there. And getting that to happen is, still a work in progress.
The fact that this is coming out now, I mean, it sounds like you have there's a critical mass of people thinking the same way. And sometimes you see the same thing happen whenever big problems happen, like we see, with AI, same as well. You have, huge declaration coming out for people to have like some type of regulatory framework around. It's coming.
Well, well, sure, that's right. I mean, and the sooner people start realizing that this is coming and they start planning for it, the better. I've been saying this whenever I give talks to, pension funds or health insurance companies or banks, or, if I were able to sit down in front of Congress, I would say exactly the same thing, that it would be absolutely the height of folly to carry on doing what they're doing now and just basically waiting and seeing on the basis that, this will just, we'll have enough warning when it does get close. It's just not true. The big reason it's not true is that the really seismic shifts in society and in the global economy will not happen when these therapies arrive. The time they'll happen is when these therapies become widely anticipated. And that could be as little as 3 or 4 years away.
And so do you think there's any danger of these breakthroughs happening within only a certain number of people having this access, or companies or countries or anything like that?
Yeah, definitely not. And fundamentally, the reason we can say that with such confidence is that the situation we're in today, where obviously the therapies don't exist, and so nobody has access to them, is spectacularly expensive. We spend a vast majority of our medical budget in any Western country goes on the health problems of late life. So truly effective preventative medicine to stop people getting sick when they get old would pay for itself many, many times over incredibly quickly. Which says, to put it another way, that it would be economically suicidal for any country to let
will get old.
Yeah, to let this be restricted in access by ability to pay. Of
Mhm.
course, I live in the USA now, where the people don't like taxation very much, and it seems to be quite difficult to think about that. But that's going to happen. And of course, the details of how health is provided are not really the point, because
Mhm.
governments can, optimize the incentive structure for everyone involved, including companies that have, essential parts of the IP, for example, just with taxes and subsidies and so on. So I'm certain that that will happen very quickly. But as I say, it'll happen a great deal less chaotically if governments actually put a bit of thought into how to make it happen in advance before the shit hits the fan, so to speak.
One of the things I want to ask you is your opinion. There's been a couple of, small studies, like, for example, the TRIM study looking at growth hormone, DHEA, metformin. I know some other small studies show like a reversal in biologic age. Do you think this is actually, and using the epigenetic clocks, do you think this is really happening? Do you think this is not happening?
So I don't want to set too much store by the readout of the epigenetic clock. And
Hmm.
even though, I'm good friends with most of the people who have developed those clocks, I think everyone accepts that, they're still a work in progress. There's still a long way to go to make those clocks really predictive of what's going to happen in the future. However, fact is that the TRIM trial and the ongoing sequel to it are great examples of cases where we have achieved genuine rejuvenation of some particular aspect of the body, in this case, the immune system, the adaptive immune system. Um, and that can be measured in a whole bunch of different ways, whether it's, um, hair becoming less gray, lots of things. Um,
Hmm.
things that are more, traditional markers of biological age. There's definitely a long way to go. The initial trial was just, open label, 9 people. It was all that could be afforded. I mean, the people paid for them. It was self-funded. Um, it's appalling that this kind of thing isn't done on a larger scale. But of course, the reason is that the interventions that are being used are, again, they're not something that anyone's going to make money out of. So we've got to do something about the fact that things that are not profitable are neglected.
One of the things that I saw in the declaration was something I wasn't even aware of. This idea about retroviruses as causes of aging. Can you just like, expand on that a little bit? Like what is our understanding about this?
Yeah, so this is a relatively new topic of interest within the field, but it certainly has a lot of merit to it, a lot of logic to it, and there seems to be good, at least preliminary evidence. So
Hmm.
a large proportion of our genome it consists of retroviruses, bits of DNA that encode genes called reverse transcriptases, such that they can be, uh, transcribed just like a regular gene would be into RNA, but then the RNA obviously is translated into a protein, and then the protein comes back and reverse transcribes the RNA into DNA again, and that DNA is inserted elsewhere in the genome from where the original one was. So we have quite a lot of machinery around ensuring that retroviruses are suppressed and that they don't get transcribed in the first place. That machinery becomes less good over time, which means that, as you said, retroviruses get essentially activated with a certain amount of transcription happening, and that transcription leads to insertion in random places around the genome of this DNA, which of course causes mutations, some of which matter. So the only real question is whether that process matters enough in a currently normal lifetime to be a contributor to normal aging. And at this point, that's a very open question. I personally am still very rather on the side of saying no, it doesn't matter. Simply because if it did matter, then it would be just like other mutations. The way it would matter would be cancer. It would be a major driver of oncogenesis. And, obviously we have to ensure, just as for every other aspect of age-related decline, that cancer doesn't happen early enough in life to stop us from reproducing. So we've got DNA repair and maintenance machinery that's good enough. And I've always said, I coined another term, namely protagonistic pleiotropy many years ago, to say that, but basically everything, all of our genome that does not have to do with the cell cycle is protected unnecessarily well, shall we say. just because it's being protected and maintained by the same machinery that is also responsible for stopping us from getting cancer.
Right, right. What do you think? I've heard about the role CMV virus may play in maybe causing chronic inflammation, probably speeding up aging. Or what's your thinking? Is this along the same mechanism you're talking about, or something different?
No, actually, that's a very different mechanism, and that's an issue that's been around for a lot longer in the field, at least 30 years or so. Essentially, what's going on there is these are viruses which don't necessarily cause mutations because they don't integrate into the genome. But even though they are detected by the immune system, these are viruses whose response to that is to go latent. Essentially, so when you've got a CMV infection, for example, then your immune system will have a go at getting rid of it, and it will mostly get rid of it, but not completely. And the virus will re-expand later on.
Mm-hmm.
This is not only cytomegalovirus, it's also Epstein-Barr virus and herpes simplex virus. It's the herpes family, often called persistent viral infections.
Mm-hmm.
Okay, what is the consequence of this? Well, these viruses tend to be not very symptomatic. They don't tend to do much.
Mm-hmm.
But what they do is they distract the immune system. So you end up with vast clones of T cells that are cognate for CMV proteins, for example. There has for a long time been a thought that these are a problem because they essentially take up the immunological space and they inhibit the ability of the immune system to activate, rapid proliferation in response to new infections that you haven't seen before.
Okay, yeah,
Now,
makes sense.
now that has become more nuanced over the past several years. Now people think that, well, if we just got rid of these huge clones of cytomegalovirus, we'd be in trouble because the CMV would no longer be addressed. And I'm sure there's some truth in that. But of course, the idea is that if we did remove the huge clones, we could certainly come up with new CMV cognate T cells, and we'd also have space to come up with other ones. So I think there's still mileage in doing something about that problem. Of course, the real thing that we'd like to do is to get rid of the CMV properly itself, which the immune system is failing to do. And there are various ideas for how to do that.
Right. Okay. Excellent. I came across the idea that hyperbaric oxygen therapy may have some impact on longevity, potentially increasing telomeres from that study in Israel. But there was this deep sea underdive. I don't know if you heard about this guy who basically stayed under the ocean for 100 days, and they showed his biomarkers, I don't know, rejuvenated, telomeres lengthened. But any thoughts on why something like that could happen?
Not really.
Okay.
Honestly, it's such an artificial environment, hyperbaric oxygen, that one's really guessing in terms of ways in which it's going to influence different aspects of metabolism. I wouldn't want to speculate beyond that.
Okay. And what about the use of therapeutic blood exchange or plasmapheresis? What's your thinking on that? I know lots of.
Okay, so that's an extremely exciting area, which has been very much at the top of our agenda in the field for about 20 years since I said, group at Stanford figured out how to do this and showed substantial rejuvenation from heterochronic parabiosis, where they were suturing young rats and old rats together for a while and seeing rejuvenation of the old rats. The idea of doing that to humans has only been explored in comedy, but the idea of doing something equivalent has very much been explored in the field. And in particular, people have focused rather strongly on the plasma, in other words, obviously the cell-free component of the blood, because you can get hold of a bunch of that from young donors, and inject it into older people.
Mm-hmm.
Now, there are various ways to do that. If you don't take out any of the old plasma from the older person, from the recipient, then there's only a very small amount of young plasma that you can put in because you don't want the person to explode. But now people are looking absolutely at, as you say, plasma exchange, and they're very much doing it clinically. Moreover, it turns out that even if what you put in is not actual young plasma, but rather just basically water with
Yeah, albumin and saline. We run
albumin,
this.
yeah.
I do the treatments on this, but I mean, it sounds like it sounds like there's a return to maybe a younger state of protein you know,
Right.
profile.
Yeah, so it's been quite a surprise to everybody that it's been so hard to figure out what constituents of the plasma or the blood are
Mm-hmm.
the real active ingredients.
Mm-hmm.
Even deciding whether the active ingredients are good things that are depleted in your older people or bad things that are enriched in older people, even that has been a really hard question to answer. And there are
Mm-hmm.
very much different opinions in the field still. Insofar as it may be good things going down, albumin itself is very much a candidate because the albumin that tends to be incorporated is not the albumin that came out of the person that you're injecting the PBS into.
Mm-hmm.
Rather, it's recombinant albumin, it's pristine. And albumin is an extremely important protein. Obviously, we have a vast amount of it. That's why we need to include it in this treatment.
Right.
Uh,
Mm-hmm.
it does a lot of things. One thing that I'm particularly interested in is its redox activity. The fact that it contributes perhaps 80% of the redox stabilization of the blood. The glutathione and so on that we often focus on more contributes only a much smaller fraction, and that could matter. So that's something that we want to test actually in our next experiment. Another thing that I think is also very important to not overlook, which we are addressing in our current big experiment,
Mm-hmm.
is the contribution of cells as opposed to plasma. So one thing that we're doing in this experiment is we are looking at mice that have had a heterochronic bone marrow transplant. What we do is, so of course, when you do when you collect bone marrow from people, you give them a mobilizing agent, GCSF, so that there's a bunch of stem cells in their blood, and you just take a blood, take take blood out of that and get the stem cells from there. What we do is the opposite. We take a bunch of mice and we just
Mm-hmm.
kill them, young mice, and isolate their bone marrow and then purify the stem cells out of that. And then we do the mobilization in the recipients, the older animals, so as to create a bunch of vacant niches in the bone marrow where the stem cells would like to be. And having done that, we then inject a whole bunch of these young stem cells, and some of the niches end up being occupied by those, so we get a certain percentage of engraftment, and it turns out to be quite good for the mice. This was done a couple of studies over the past several years that came to our attention, and so we thought we'd have a go. And it turns out it works quite well in synergy with the other treatments that we are giving these mice.
I'm wondering if in people who are, let's say older people who have received a bone marrow transplant from a young individual, do we see any health benefits? Like over
Yeah,
and above?
you are by no means the first person to ask that question, and I honestly am quite surprised that we don't know the answer. Nobody has come forward and provided an answer to that. I think it's probably because the way in which we're doing these experiments in mice is non-myeloablative. We're doing this mobilization thing, where the typical bone marrow transplant in humans is after lethal irradiation, right?
Mm,
When they've got leukemia or something like that, right?
yeah, yeah,
So it's
yeah.
not really, it's a bit apples and oranges.
Yes, makes sense. All right. I know we're just about ending the time, but I want to ask, you look like you're like reversing your aging over. See if you
Well,
haven't aged.
you're very kind. I don't often feel that way. But
But what do you do yourself? I mean, now you have knowledge probably, more than anybody else on the planet about what's happening in this space. So what do you do yourself?
yeah, honestly, I'm the wrong person to answer that question because, first of all, I actually don't look after myself all that well. I mean, I definitely don't smoke. I don't get seriously overweight, and I do have a good diet. But the other thing that's a big factor that everybody points to, which is getting enough sleep, is something that, I do a lot of traveling. I'm short of sleep a lot of the time.
Mhm.
So I don't look after myself ideally. But,
Mm,
the thing is, I'm just lucky. I'm very well built. I
mm.
can drink exactly what I like and nothing ever happens, and I don't even need to do any exercise, and I still stay wiry. So, don't do as I do as I say. Just like,
You're
and of course,
counting on that. You're counting on being around for the next 20 years, see if we can take advantage of
Well,
these
I'm
changes.
hoping so, but the point is, everybody's different. Everybody's metabolism has its own strengths and weaknesses. And so honestly, the only generic advice that I feel like one can give in terms of maximizing one's healthy lifespan is to pay close attention to your body and
Mhm.
to figure out, what's going on, what's not going on. Gluten intolerance is something that I think is a great example of this. Lots and lots of people find out late in life that they are somewhat gluten intolerant. They've been putting up with it without knowing it for decades, right?
Right.
So, I guess, I think, this is a little bit creative on my part because I'm definitely a PhD, not an MD, but I honestly can see a strong argument for just recommending to absolutely everybody that they should eat gluten-free food for like a fortnight, like a couple of weeks,
Mhm.
just to see whether they feel different, you know?
Right. Yeah, that's a very, very good point. What do you think about the area of microbiome on longevity? I mean, they said 10 times more cells of the microbiome exist in human cells, and maybe that's a whole other area.
So it's definitely an area that needs to be explored more. It has become pretty fashionable, so the work on it is increasing exponentially right now, and we'll know more as time goes on. But at the moment, I don't really think that we need to address it all that much. Not in the long term. In the short term, it may very well be beneficial to optimize one's microbiome in whatever way. But in the long term, the thing about the microbiome is it consists of single cells
Mm.
that are constantly undergoing natural selection. We have the microbiome that the environment that these bacteria find themselves in uh, most fits. As such, it seems to me that if we fix everything else in the body, the actual human cells, then the
Mhm.
microbiome is totally going to fix itself. And we don't
Mhm.
need to figure out how to fix the microbiome directly.
Yep. Okay. Well, thank you so much. I really appreciate your time on this holiday Monday. I really appreciate it.
Well, it's my pleasure. Thank you for having me.
So there you have it. That's today's talk with Dr. Aubrey de Grey. I hope you enjoyed it. Lots of nuggets in there about different mechanisms of aging and what the current state is right now of longevity research. He does believe that, within the next 15 years, we're going to be at that point where we can probably get to escaping longevity escape velocity. So I hope you enjoyed it. If you liked it, please like and subscribe to this video, share with your friends, just so that way we can provide more of these type of amazing speakers for you. All right, we'll talk to you soon and take care.